Welcome to this lecture series in linear algebra. In this lecture, we'll define the determinant of an endomorphism on a vector space, and let us recall what we need. So we will need the change of basis theorem, which we discussed long back. What does it say? Suppose we have an endomorphism on some vector space, and suppose we have two bases, b and b prime, of the vector space V. Then we can define two matrices. We can define the matrix of T with respect to B, and we can define the matrix of T with respect to B prime. And naturally, a question arises, how can we relate these two matrices? And in change of basis, the lecture on change of basis, we showed that there is a matrix, let's call it P, such that this equality happens. And in fact, we can explicitly describe P, but let me not do that since we don't need to. So a matrix with respect to one basis, or rather I should say the matrix with respect to one basis and the matrix with respect to the other basis are related by such a transformation, right? There exists a matrix P such that this conjugation operation, this is called the conjugation with P, anyway, doesn't matter. So this is the change of basis theorem. We will use it. And yeah, I think this is what so this is exactly what I've written here. I should have just referred to this. So you can read out the full statement. And in the previous lecture, we defined the determinant of a square matrix. So I don't want to recall it in great detail, but if you have a square matrix, every column gives rise to a vector in the corresponding coordinate space. Suppose it is a matrix over a field F, then every column gives rise to an element of F to the n. There are n columns, so we get n elements from F to the n, and then we can use the definition of determinant that we had originally. So the determinant of a square matrix is defined in this fashion, and very interestingly, the determinant of the product of two matrices of the same order, since we are producing two matrices, both of them are square matrices, and if you take the product of them, the determinant of that is the product of determinants. This is what we proved in the previous lecture, a most important property about the determinant. And as a consequence of this, we saw that the determinant of the inverse of a matrix is the inverse of the determinant. So suppose we have an invertible matrix A, then the determinant of the inverse of A is the inverse of the determinant of A. Immediately follows from this formula. And we also saw that the determinant of a block upper triangular matrix can be calculated in a certain way. In the lecture, I called it a block diagonal matrix, but the correct terminology for the matrix was block upper triangular matrix. I mentioned a correction of it in the lecture also, in the sense that I added a correction to it after uploading the lecture. So we will also use this at one point. And now let us proceed. Here are two problems for practice. This should have been given maybe a long back or something. In fact, these are more relevant in the next lecture or next to next lecture. These are not really relevant right now. Maybe I'll repeat them. I am stating them here, but maybe I'll repeat them in the next lecture. All right, so let's proceed. So we want to define the determinant of an endomorphism. And before we give a formal definition, let us see at least some geometric motivation behind the definition. So suppose we have this R2, and these are the standard basis vectors of it. And there is a linear transformation which takes E1 to this vector and E2 to that vector. What the determinant of T is trying to capture is the volume that you get of the parallelogram that you complete. So let me say that again. These two vectors form a parallelogram. It has some area. I'm calling it volume, but in 2 dimensions it is the area. Originally, the area was 1 unit. Now the area is something. That is what the determinant of T is trying to capture. Right? So that is the idea, but the definition that we will give, the formal definition will not immediately capture that or seem to capture that, because the general definition is over an abstract vector space, not on a coordinate space. On a coordinate space, it's very easy. I mean, what we are saying is easily capturable. But for a general arbitrary vector space, which does not come with any standard basis, R2 comes with a standard basis. Any coordinate space comes with a standard basis. So we can speak in this language. But for a general vector space, there is no standard basis, which is why the definition may look a little bit obscure. But let's get into it. So fix a vector space V over a field F and fix an endomorphism T on the vector space V. Then the determinant of T is defined as the determinant of the matrix of T with respect to B, where B is any basis of T. Of the vector space V, not T. So what's going on? We had an arbitrary or abstract vector space over a field F. Since it does not come with a basis, we first pick an arbitrary basis, whatever basis we like, and we find out the determinant of the matrix of T with respect to that basis. This is something that we defined in the previous lecture. This is what we are defining now. Even though the spelling is the same, the operator or the function is different. This is operating, or the domain of this function is that, while the domain of this function is set of all the n cross n matrices, where n is the dimension of V. So let there be no confusion about that. So the determinant of T is defined as the determinant of the matrix of T with respect to any basis. But now immediately a question should come in your mind. Why is this well defined? What do I mean? Well, a vector space has many, many bases. If F is an infinite field, it might even have infinitely many bases. So two different people may choose two different bases and compute this thing. Somebody may choose a basis B, somebody may choose a basis B prime. Then one guy would get determinant of the matrix of T with respect to B, and the other guy would get the same thing with respect to B prime. Why should those two numbers be, or field elements be, equal? Why should those two quantities be equal? Unclear at this point. So in the next page, we will show that this is a well-defined thing. Meaning, it is independent of the choice of the basis. No matter what basis you pick, this quantity is the same. So once we prove that, we would have a well-defined notion of the determinant of any endomorphism on a finite dimensional vector space. Okay, so let's get into that. Very simple. It's going to be a very simple thing. It will only use the change of basis theorem and the formula for the determinant of the product of two matrices. Okay. So what does the theorem say? It says exactly what we said in the previous slide. Fix any endomorphism on a vector space V. Fix two bases of the vector space V. Then the determinant of the matrix of T with respect to B is same as the determinant of T of the matrix of T with respect to B prime. So let's immediately prove it. So say n is the dimension of the vector space V, and we know by change of basis, we know that there is an invertible n cross n matrix over F, where F is the base field of the vector space V. So F is the base field of the vector space V. As usual, we suppress all of that from this notations. So there is an invertible n cross n matrix P, which is over F, meaning the entries of the matrix P are coming from F, such that the matrix of T with respect to B is equal to P times matrix of T with respect to B prime times P inverse. And therefore, the determinant of the matrix of T with respect to B is equal to the determinant of the right-hand side. But what is the determinant of the right-hand side? It is the product of the determinant of the three things. Give me a second. The determinant of the matrix of T with respect to B prime times determinant of P inverse. But the determinant of P inverse and the determinant of P are inverses of each other. This is 1 upon the determinant of P. So they cancel out. We cancel them out. And that's it. We get the determinant of the matrix of T with respect to B is same as the determinant of the matrix of T with respect to B prime. And that's what we wanted to prove. So this establishes the well-definedness of the determinant of any endomorphism. And now let us proceed. So now we'll show something very important, that the determinant of the composite of two endomorphisms on, so we have two endomorphisms S and T on a vector space V. The determinant of their composite is the product of their determinants. And this is just a consequence of the fact that the matrix of the composite is product of the matrices. So fix any basis, let B be an arbitrary basis. All right, and let and we know that the matrix of the composite with respect to B is the product of the matrix with respect to B of S and the matrix with respect to B of T. And this equality is actually what motivates the definition of matrix multiplication. You could say that. Right? I mean, this is what we discussed when we were discussing matrices. So we have this equality, and therefore the determinant of the right-hand side, but the determinant of the right-hand side is product of the determinants, which is, yeah, so what is this guy? This guy is the determinant of the composite. Therefore, the determinant of the composite is equal to the determinant of S times determinant of T. Why is that? Because this is by definition the determinant of S, and that is by definition the determinant of T. And this is by definition the determinant of the composite. So that's the proof, very simple. The difficulty is, of course, in this step. The entire mathematics went in this step and also in this step, but mainly in this step. But we proved it in a previous lecture. Okay. So now we will finish this lecture with just some basic properties of the determinant of an endomorphism. Note that the determinant of T is an endomorphism on V. The determinant of T is non-zero if and only if T is invertible. Okay, why is that? Well, T is invertible if and only if, note that, or we know that. So fix a basis. We know that T is invertible if and only if the matrix of T with respect to B is an invertible matrix. Right? And we have previously seen that the determinant of the matrix of a transformation, the determinant of a square matrix is non-zero if and only if the matrix is invertible. So that's it. I mean, once you just see that this is equivalent to saying this, and then you use what we proved about matrices, you will see that this is true. So if the details are not completely clear, take this as an exercise. All right, the second one. You scale an endomorphism. The determinant scales by the nth power of lambda, where what is n? N is the dimension of the vector space. And again, the reason is very simple. Just convert this into a matrix equation. So B is again some fixed basis. Just observe that. Maybe I'll not write the full details. We just know that matrix of lambda T with respect to a basis B is lambda times the matrix of T with respect to B. just this equation, and then your knowledge about the determinants of square matrices leads to this conclusion. Okay, lastly, suppose we have a vector space. So suppose our vector space V can be decomposed in this fashion where U and W are T invariant subspaces. Then the determinant of T is the product of the determinant of T restricted to U times the determinant of T restricted to W. Okay? Why is this? Well, choose a basis. Let B and C be bases of U and W respectively. What does that mean? It just means that B is a basis of U and C is a basis of W. And now if we arrange B and C side by side, that becomes a basis of V. Right? Since V is the direct sum of U and W, just this list of vectors appended by this list of vectors forms a basis of V. And that is what we will refer to as this thing. So this is just a notation, I believe a fairly standard notation, which is appending the two lists. This is a list, that is a list. You just write down the elements of this list side by side with that list. That becomes, that by notation is equal to that. So yes, B is U1 up to UM, or let's say UK, and C is W1 up to WL. Then this is, first you write U1 up to UK and then you write W1 up to WL. So that is the basis of the vector space V. And what is the matrix of T with respect to this basis? It is a block diagonal matrix, where the first block is matrix of T with respect to, rather the matrix of the restriction of T to U with respect to the basis B. That is the first block. It's a square block, but it kind of is hard to make it look like a square. It's too long. Let me try though. That is the first block. Still not a square. Yeah. All right. And what is the second block? That is the second block, and just those two blocks are there in this block of a triangular matrix. And let me make one point very clear, that even though in the figure it seems like this matrix and that matrix have the same width or same dimension, that is not necessarily the case. The width here is same as the dimension of U, and the width here is same as the dimension of W, so they may be different. Okay, so the matrix of T with respect to this basis is that matrix. And in the previous lecture we commented that the determinant of such a matrix is the product of the determinant of these two things. In fact, here there could have been any garbage, that wouldn't have changed anything. So the determinant of this matrix is the product of the determinant of that and the determinant of this. But if you just now use the definition of the determinants of endomorphisms, you will see that what we just said is exactly this equation. The determinant of this is the determinant of T. The determinant of this matrix is the determinant of T restricted to U. And the determinant of this matrix is the determinant of T restricted to W. So that's it. Okay. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.